So in the first lesson, we were talking about a chi-square goodness of fit, okay? And what that does is that it basically tests if the distribution of a categorical variable, like, and we used race because we were talking about Harvard, okay, is the same or different than what we would expect. And then we calculated that chi-square statistic. If it was very high, it told us there was a difference. If it was very low, it told us there was no difference. But it was only referring to one categorical variable. Now we're going to talk about a chi-square test for what we call independence, or two-way tables, or two variables. Okay? So this is no longer one variable. We are looking at two different variables to see if they are related or associated with each other. And this is an example that we used quite a long time ago about the stop and frisk program in New York City. Okay? And you can see here in this table a number of Black, Hispanic, and white people were stopped. And three things happened when they were stopped. There was no force used, okay? Hands were used, or there was a higher force level necessary, according to the police. Okay? And obviously it makes sense that no force used, there would be the higher numbers there. And then if there is some force used, there would be lower numbers. And then you'd get pretty, I mean, it's still significant numbers, but you wouldn't expect as many higher force level interactions. Okay. So just a reminder, the stop and frisk program, it allowed police officers to stop people on the streets. Just say, I'm stopping you, searching for weapons or drugs or anything like that. Okay, and it was controversial, and critics said that, you know, it led to discrimination by police, people of color. Okay, so what we're going to do is fill in the table. We're going to focus on black and white here for the time being. So no force used. There are, so we're going to do a conditional distribution. So we're going to take the amount of people in which no force was used, black people, over the total number of black people. So in this example, or in this cell, sorry, 1,371 black people were stopped, but no force was used, over a total of, and if I add those three numbers up, I get 1,743. And that works out to approximately 78.7%. And then I would do 263 over 1,743. And then 109 over 1,743, and get those percentages, which would be 15.1%. Because it's always better to deal with percents or proportions than it is to deal with just raw numbers. Okay. And then we'll do the same thing for the white people. So if we add up all these people, we see that there are 300 in total. 260 of them, when they were stopped, no force was used. So 260 of the 308 gives us 84.4%. 30 of the 308, some force was used, or hands, or that percentage is 9.7%. And there were some in which more force was necessary, 18 out of 308 for the white people, and that's 5.8%. So you can see how people can manipulate things. even just something as simple as this, just by focusing on numbers instead of percentages. So a television commentator says police had no force interactions with only 260 white suspects. However, a higher number of black suspects, 1371, did not experience force. So what the commentator is saying, clearly black people experience force-free interactions with police more frequently than white people. Like, what's wrong with that? I mean, yes, I suppose you could say that just by looking at these two numbers, but what tells a different story? The percentage, right? There's actually a higher percentage of white people that encounter no force interactions than black people. Okay? So the numbers are technically correct. Nick. But it's not a good analysis. By just focusing on raw numbers. By focusing on raw numbers. Because if we look at the percentage, or at the percentages of no force, white people experience a greater percentage of no force. So that's why you should, and remember what I mean by proportions? A proportion would be 0.787. A percentage is 78.7%. So usually when we talk about proportions, I mean, you could talk about it in fraction form, but it makes a little bit more sense in decimal form. So imagine a statistician is investigating if there's convincing evidence. This is a similar question to what I gave you guys in the last lesson. Okay? We could perform a series of Z tests on each level of force. Right? So we could perform a Z test on this to see if there was a difference between level of force used and race. And then we do one on this, and then we do one on this, but that's the problem of multiple tests. When you start doing too many tests, because remember, whenever we do these tests, there's always a 5% chance that we're wrong. That's what 5% significance level means. So if we do, the more and more tests we do, chances are one of our results is going to be wrong, which is why we want to do a single test in which the probability of being wrong would be lower. So again, first, it's inconvenient to do lots of tests. Second, and really more importantly, the more tests you do,
the greater chance one of your tests will be in error. Whether that's a type 1 error or a type 2 error.
Remember, a type 1 error is when we reject the null when we shouldn't have. Type 2 is we didn't reject the null, we failed to reject it when we should have. And because we're dealing with two variables instead of one variable like we did in 9.1, we're going to do something called a chi-square test for independence, which is pretty similar to what we did for goodness of fit. It follows the same steps. It's just our expected counts when we do those involves a little bit more calculation, and the graphing calculator portion is slightly different because we actually have to enter a matrix or an array of numbers. Okay, so here's our hypotheses. The default, no association, no relation. Status quo, no relation between race of suspects and levels of force used. Okay. Used, level of force used at the same rates. What we're trying to establish or see, there is an association. Between race of suspects and level of force used. This is the alternative, and we're trying to see if force is being used at different rates. So you see, we've kind of set it up as a simple hypothesis test, rather than doing a series of tests. So we start by, and again, this is very similar to the previous lesson. We start by assuming the null hypothesis is true. What exactly does that mean? It means we assume force is used at the same rates for each racial group. So if we assume if it's actually in fact true, how likely is the data that you have gathered? Okay, so what we have to do is we have to compare the distribution of force rates across races in our sample data. Remember, we took a sample. See how different or similar they are. If our sample is very different, that suggests one thing. If our sample is very similar, that suggests another thing. To see how they are. So, and like I just said, if different enough from our sample to what we would expect, we have evidence
force levels are used at different rates. Between racial groups.
So now we're going to go ahead and calculate the chi-square statistic, and remember the formula, and it is a formula that you will get. We have to find the difference between the observed value and what we would expect. So we find the difference between those, square it, divide it by the expected, and then add up all the ones in the table. So here's our observed data. This was from the sample we did. Okay, a sample of 3,164 stops. We have to figure out what would we expect to happen. Okay, and to figure it out, so let me just take one of these as an example. We want to figure out, okay, in our observed data, we saw that 1,371 Black people were stopped but encountered no force. We want to see how many would we expect that to happen to. So how do we figure that out? Well, first of all, we have to figure out how many Black people are there in the total. So I'm going to do 1743 divide 3164. That tells me, and if you do that, okay, well, I'm going to kind of do it up here and down here. 1743 divide 3164 gives me about 55.1%. Okay. So we would expect in the total number of no force, 55% would be Black people. So what's the total number of no force? What's the total number of people that experience no force? 2,484. So then we would have to do 55%, 0.1% of 2,484. So really what I'm doing is I'm finding the percentage of Black people in the group timesing the total number of people that didn't experience any force. That's why I wrote here column total times row total divide grand total. Okay? Because it's 17 for Black and no force, it's 1743 times 2484 divide 3164. But I was just showing you here how exactly we get one of them. And you can see that it works, this will work out to 1368.4. So this works out to 1368.4. So that's what we expect. How many Black people would be stopped but no force would be applied? This is how many happen, pretty close to each other. So you'd have to do the same thing for the other 8. Okay, so I'm just going to write, I'm not going to write, I'm just going to give you the answers to most of them. But so for this next column, okay, we would do, well, the total percentage of Black people stopped was this. The total number that had some force or hands is 481, so that's what I times it by. And in this one, I get 265 people, is what I would expect 263 is how many? Do you see how we're calculating all of those? So I'm just going to go ahead and write the numbers in the rest. So this works out to 109.6. This works out to 873.8, 169.2, 70.0, 241.8, 46.8, 19.4. So in general, it looks like what we would expect the people or the type of force applied and the racial group looks very similar to what we observed from our sample. Some were a little off. Like for Black people, it was pretty close. For white people, a little off by about 18 here, 17 here, 1.5 there, not very much. Okay, so they're pretty close to each other. So like I said, that's is that one there. So just like I talked about, compare the expected counts to the observed data. Well, like I said, Black people was pretty close. Hispanic, we would expect more to have no force than actually did. We would expect less. So it looks like here for Hispanic, the actual people that experienced hands or even greater force was higher than what we would expect. Okay. Whereas for white people, it was lower for hands. And you can analyze all of these cell totals. But in general, pardon me? It could be in there. Yeah. So, no, that's white people. Receive less force less frequently than expected. And no force more frequently than expected. Expected and observed counts for Black people, like I said, it's an and. Observed counts for Black people was quite close. Well, in order to be more statistically sure of this, this is where we have to calculate the chi-square. And doing it the long way is really long. Because what you would have to do is for each one, each of the 9 cells, you would have to take the observed
minus the expected, square it, divided by the expected,
And then do the next one, and 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 add them all up. Okay? Obviously, that's very time consuming. So we're going to see that we have a graphing calculator function that does it for us. But just to sort of start it, we would have to do, so this is the top left corner cell for each table. Observed minus expected squared divided by expected plus, and then you'd have to do the same thing for the other 8 cells above. So you would get 9 values to add together. And when you did that, you would get approximately 10.17. It doesn't really tell us a heck of a lot. Okay? I mean, is that high? Well, I don't know. But remember, and we talked about this before, when the chi-square statistic is large, that means your observed data is very different from what is expected under the null. Okay? Which means it would be very unlikely to get a sample like that, which means it would have a low probability value. If the chi-square is small, that means it's going to be very similar. Okay? Which would equate to a higher p-value. Which means you would not reject the null. There's really no difference. But let's go to the graphing calculator function and the 4-step process. Okay, so again, long way, that would take an awful long time to do. But here, okay, we've got the, this is our sample. And it says to the right, 3164 total out of over almost 700,000 stops, 2011. We want to see if they're convincing evidence. So first thing, state. Well, or no. No association. Between race and force cell. Notice we don't have to define any variables between race and. What we're trying to establish an association between race and force cell. Or is an association. Is an association. Just remember we're at the 0.05 alpha or significance level. So plan, conduct a chi-square test for independence. Independence just means we're dealing with 2 categorical variables. Yeah. And then we've got our 3 conditions. Just remember the large counts was slightly different, right? So remember, when we're dealing with categorical data, we're talking about proportions. So just remember, because we're talking about proportions, that's why we use large counts. So we use random, 10%, large counts. We don't use large sample because we only use large sample for means, which is a quantitative variable. So random said records randomly sampled. %10 condition. Well, our sample size was 3164, and it said how many stops were made? Almost 700,000. Well, 3164 is definitely less than 10% of 685,000 stops. The large counts, you've got to use all your expected values from the table. You've got to use all of these have to be greater than 5. Okay, greater than or equal to 5. So if you look at all these, I'm just going to simply say all expected counts, all 9 expected counts are greater than or equal to 5. Remember, when it's chi-squared, 5. When it's proportions, 10. Okay. For the do phase, we're going to see something different. Right. How do we enter a table? We've entered lists, but how do we enter a table? Well, how to enter a table, we use something called a matrix or an array. So if you go to second, and then the X to the -1 button, which above in blue says matrix. So we want to enter the values for a 3 by 3. So we are going to, what am I doing here? Wait. Second matrix. Oh, edit. That's fine. I'm on the wrong one. Yeah. So we press enter, and then we want to do a 3 by 3. So 3, enter, 3, enter. And you can see it gives you a 3 by 3 table. And all you have to do is enter all the, all the observed accounts. So from here, enter all these into this. So you can go across or down. So 1171. It takes me across by default, so I'll just keep doing that. 853, 260. No, I said 1371. I don't know, maybe I said something. I was thinking 1371. 109. Sorry?
It just takes me back to the end.
Okay, hang on, just sit there. Yeah, once we enter all these, just look at the instructions here. So once you've got that, so we want to go to stat, go back to our tests. And we want to find just a chi-square test, not goodness of fit. Okay. And notice the observed is matrix A, which we already entered. Okay. Do we have to enter our B? Wait. Did anybody get the answer?
Go back to the matrix and then.
Do you have to do the, oh, wait a minute, did I already do mine? See, mine gave me the answer right away. Oh yeah, because I already have my, yeah, I've already entered my, well, no, it should have all the expected counts that we covered. It does? Okay, so it did it for you, right? It calculated the expected counts for you. So go to stat, go to tests, chi-square test. The observed we entered, it was matrix A. The expected was entered, calculated for us. It was matrix B. Calculate. And you should get x squared equals 10.17, etc. And our p-value is 0.3759, etc. What's that? 0.03759. Okay. So to show your calculator speed or your calculator, you would do this. So we need to show the matrix that we've entered. That's just entering the table that we're given, the sample data. So you would just like this. And then we did a chi-squared test where the observed was matrix A. Expected was matrix B, which was calculated for us. Where we calculated it longhand, but the graphing calculator did it for us. So, I mean, you can get the chi-square, but we're focusing on the p-value because that's what we use to make our conclusion. So our p-value, if I round it, is approximately 0.038. So our conclusion, because our p-value is less than our alpha value, B what? The HO. Rejected. We reject HO, that means we have convincing evidence of whatever the original question was. So you just have to go back to the question. We have convincing evidence of an association between racial group and force level. The very last thing I want to do is just to make you aware of another chi-square test. We're not going to do it. Something called a chi-square test for homogeneity. Okay. The independent system, the independent situation we did today,
there are two variables.
Race of suspect and force level.
And there was one sample from one population, which was New York City.
For a homogeneity, homogeneity is kind of a combination of the independence and the goodness of fit we did. Okay?
It's one variable like we did in 9.1,
But it's for three different, or sorry, it's for, in this example,
three populations. So just as to show you the difference between the two,
here's the one we did today. Here would be an example of a homogeneity situation. Okay? Where we're given a breakdown of race of suspect in three different populations, three different cities. There's only one variable here, race, but there's three populations. There's two variables here, one population.
so the hypotheses in each of these situations would be HO, no association, between race and force level. Alternative would be is an association. Between race and force level. That's one. The only difference in race in stops in NYC, Boston, and LA. Okay. The alternative, there is a difference in race in stops in those three populations.
And this is kind of just, I'm not going to read this. In your own words, what makes it an independent situation? Well, this is what makes it independent. What we set up here. That's what makes it independent. Two variables, one population. What makes this one a homogeneity?
One variable, categorical variable,
But two or more different populations. In this case, three, but it could be four populations, five, as long as it's two or more. Okay. So I'm not going to rewrite that.
You guys go back to the conclusion on this.
Sorry?
Can you go back to the conclusion part?
You mean on the previous page?